To introduce Kristen Persson from Lawrence Berkeley Lab. She's a staff scientist there and in charge of the materials project, which I will describe somewhat superficially as Facebook for molecules, where molecules can go to find other ones with whom they can have positive interactions. And so we'll hear more about how all that works.
It's a pleasure to be here. I'm excited to give a lecture that is just for the people in the audience as well as online. So I'll be describing what high-performance computing can do and cannot do for material science and how we can leverage that and become an online resource. It's accelerated materials design through high-throughput first principles calculations and data mining. So the outline is that I'll give a brief overview or sort of motivation of why we're doing this. I'll vary some few slides on a crash course of the implementation or the casting of the Schrödinger equation that we use, which is called density functional theory. Then I'll talk about all the problems of running DFT codes on high-performance computing centers and what we've done to make that work. So it's not an exascale poster child. Then once we've solved the computing, I'll talk about some of the cool stuff we can do with these kinds of calculations, how we can apply it to hopefully real-world problems. And at the end, I'll talk about how we made this into the materials project, which is this Facebook for molecules that Jim talked about. So I don't know how often you think about the importance of materials in your everyday life, your laptops, your phones, the fact that the batteries have been getting smaller and smaller since we had the first phones that were this big. I remember walking around with a phone this big, a cellular phone. Now they're very small. Some of the things we're doing today couldn't be possible without the development or the optimizations of materials. For example, we send signals across long distances without perturbation. That enables the information technology we have today. And the reason that people can do that is because we found out that defects in certain glasses perturb the signals. If you remove those defects and make really high purity glasses, that's when you can send signals across long distances. So as communication, today we're building airplanes and even bridges out of carbon composites, not out of steel and concrete anymore, which hopefully they think is going to make it cheaper, long-lasting, and also easier to build. And there are a number of other examples. I personally like the nylon story from the Second World War. DuPont was charged with making a very, very durable and high-strength parachute for the troops. But of course, at the end of the World War, the Second World War, they realized that they were sitting on a gold mine. They made a lot more money selling it as nylon stockings than as parachutes. So these are all materials problems where you come up with new materials that have enabled complete societal changes or changes how we do things. So that's what I do. That's what I want to do with my life, come up with new materials and hopefully do it better than we've done it before. Because the sad news is that it's really hard to come up with new materials. Let's take an example. Edison in the 18th century, sorry, the 19th century, when he was looking for a filament, the little thread that burns in a light bulb, he just tried a bunch of stuff. That's called an Edisonian approach. And he actually ordered materials from all over the world, more than 3,000 materials. And he just tested them, one after the other. That's why we call things Edisonian. There really wasn't much of a design. He just wanted to see what is the best material out there. The really sad part of it, he didn't find the best one. The one we use today in these old style light bulbs is tungsten, and Edison suggested a cotton-based bamboo material. That's the light bulb material he went for. So can we do this better? Well, let's see if I can make this movie run. This is how Tony Stark come up with materials, and this is kind of the end of where we want to go. He renders the periodic table using Jarvis, and then he, I think, uses his intuition, plucking a few of the elements from the periodic table, and then he synthesizes it with his hands in the computer. Sure, it's all due to Jarvis, right? He bounces it around a bit to feel the properties, I suppose, and then he puts it into his suit to check for biological compatibility. And it's all done in 30 seconds. Brilliant. That's the goal. That's where we want to go, right? We don't want to do the 3,000 materials, order them from all over the world, try one after the other. It took years. This is the end game. Unfortunately, we're a little closer to Edison still than we are to Tony Stark, to Iron Man. If we look at all the things we'd like to make a progress in, like photovoltaic. We'd like to generate electricity from the sun in a more efficient way without covering the whole, Arizona desert with PV materials. We'd like to have transparent conductors that are part of those panels. We'd like to have better permanent magnets, not to be dependent on those very, very sparse rare earth metals that we find mostly in China. We'd like to have solar fuels, thermoelectrics, energy storage. The list goes on in order to make sustainable energy production and storage a reality. The sad news is it takes about 18 years from the time a material is discovered in the lab to being commercially successful. So think about that for a moment. Discovered in the lab. That means it's actually made to work in the lab. It's not from the day you had a great idea and you went off somewhere. It's from the day that most scientists think they're done. We publish, we patent, we say, go do. This is 10% or 20% or 30% better than what's out there. They're immensely proud of doing that because it's a hard problem. But even then, it takes on average 18 years. And the list goes on and on. These are just some of the applications where this has been proven to be the case. And the reason for this, according to at least a long study made by DOE as well as the former president of MIT, is that we don't know enough about the materials when we propose them. So when they say they work in the lab, they work under specific conditions. We have not tested everything. They may corrode when you put them in the right environment for which they are supposedly designed to work. They may have other issues. They may be temperature sensitive. All the things that need to work when you put it in a real application that we don't know about them. We know them under very, very controlled circumstances. So if we find out more about the materials, that's one way of shrinking this timeline because we really don't have 18 years for most of these technologies. So how do we get more information about materials? This is where quantum mechanics and calculations can help us because in the last 20 years or so, we've been able to cast the Schrödinger equation, which tells us how matter and physical interactions work, in a form that is actually computable and can be computed fast using today's computers. We'd like to get here with engineering properties, but unfortunately there are very few sort of quantum operators that just gives you the full answer at the end of the day. So you have to be able to go from the quantum mechanics through some sort of translation layer. I can get energies, I can get trajectories, I can get stuff like that from the Schrödinger equation, but in the end I have to translate it to engineering properties. So I'll tell you a little bit about how we've done that and how that's possible. Not for every single property. I'm not one of those people who will say we can compute everything because we can't yet, but we can compute enough to make the process of discovery and hopefully optimization a little shorter. So that was the motivation. Let's see if we can describe a little bit of what density functional theory and the Schrödinger equation can do. So first principles, that's the same word as ab initio. It means from the beginning. It means that there are no adjustable parameters in principle, at least not on the physical interactions. So it means that you can start from the atomic numbers of a material. If you have sodium chloride, you have sodium in the periodic table, and you have chlorine in the periodic table. And if you put those atoms somewhere, you should be able to calculate the properties of sodium chloride just from the atomic numbers and knowing the amount of nuclei and electrons. So we solved the Schrödinger equation. This is the time-dependent version of the Schrödinger equation, which we can use, but we can also use the time-independent one for static properties, for things that don't change. And then from that, we predict the physical and the chemical properties of the systems we're interested in. In this particular case, there's a nanoparticle, but we can do simpler systems than that too. We tend to go after standard DFT, the steady state properties, so things that don't change under time. So if you want to know the ground state properties of materials, if you want to know the ground state properties of sodium chloride, for example, that's a steady state. It doesn't change. If you leave some salt on the table, it's not going to evolve to something else, even if you leave it there for a long time. That's a steady state. And it's just from your perspective, it's an eigenvalue problem. You have a Hamiltonian that tells you about the interactions and the energies that goes on in the system, and that should correspond to the lowest energy of the combined system. So the way that we approach this is that we have a number of nuclei and electrons. And usually you want to put them in some sort of positions that make sense from the beginning. If you just bunch them together wherever they are, if you put the sodium very far away from the chlorine, it takes a long time to find that ground state where they're just sitting in the crystalline salt version. So you want to start with a good initial guess of where they are. But once they are in the initial guess, then you really just want to cast it in the form that you have a Hamiltonian operating on the wave function, and then the energy times that wave function. The Hamiltonian is basically just the sum of the energies or the interactions in your system. So you have the kinetic energy for the nuclei and the electrons, and from the nuclei-nuclei interactions and the nucleus-electron interactions and the electron-electron interactions. Basically everything you can put your hands on to characterize the system. Some of these terms are fairly easy to compute, and some are harder. And that's really the whole secret to density functional theory and why it made a difference, going from the Einstein version of the Schrödinger equation and Schrödinger to today's formulation. The nuclei-nuclei interaction we can separate out. It's independent of when the electrons work, and that's really a good idea because the nuclei and the electrons, they move on different timescales. The nuclei, if they move to a little bit different position, then the electrons find their ground state very quickly. So you can separate those two parts of the Schrödinger equation. But the electron-electron interaction is a tough one. That's where we have to make some approximations in order to at least even compute it. Because the number of mathematical equations that we have to solve increases exponentially with the number of electrons. And these electrons have many body interactions. If I have 2 electrons like this, they interact, and if I have a third one up there, then it's a 3-body interaction. And these are fairly difficult to deconvolute from each other. So even with modern supercomputers, we can really only solve exactly the Schrödinger equation for a system of 4 to 5 electrons. Even if we put the worst beast out there on the problem, it takes weeks or half a year. So we have to make approximations. And the way that the density functional theory does it is it basically takes the electrons and the form where they all interact with each other through very complicated interactions and cast it into a 1-electron problem. It takes all the electrons and sort of, you say, we create a potential from all those, and every single electron moves in the potential from the other electrons. So it's sort of a, it's a simplification of the problem, and it approximates the many-body interactions, which we call the exchange correlation energy. It contains the Pauli exclusion principle and all those things you've heard about in quantum mechanics. And it creates, so we have to cast things in what we call this effective potential. This one here. All the magic basically sits in that part. That's the approximation to the Schrödinger equation. And it's really because the people came up with the local density approximation or the GGA approximation that we can solve this and that it works fairly well. Kohn and Popel got the Nobel Prize in 1997, I believe, for discovering this way of casting the Schrödinger equation. Not for coming up with it, but casting it in a way that we can actually solve it fairly easily, and that the approximate part to the many-body interaction can be a very small part of it. And that's what they separated out in this effective potential.
Question?
Yep.
What about the nucleus-electron interactions? I noticed that was missing on the previous slide. Does that get ignored?
No, not at all. But what we do is that something called the Born-Oppenheimer approximation, where we say that once we've moved the nuclei to some position, the electrons find their ground state instantly. They move on different timescales. So they sort of decouple to some degree. You have the, yeah. So once you have this formulation of the Schrödinger equation, we can compute a lot of different properties. And this has evolved tremendously in the last, I would say, 15 years. When I started as a grad student, we were still dealing with calculating properties of a single element using DFT, and we were still optimizing functionals. We're still doing that today for this exchange correlation function. But today we can actually use supercomputers with the same formulation of the DFT to calculate very, very complicated properties, like some of them listed here. Phase diagrams. This is the phase diagram of lithium iron phosphate, which is a quaternary phase diagram. Diffusion properties of ions. This is lithium diffusion in graphite. Voltages for batteries. Particle morphologies. Basically, if you make sodium chloride, which form will the crystallites take if you just make it in an oven or something, or out of a solution precipitates. We can calculate, see if I, oops, sorry. Band gaps, although that's one of the harder ones. And reaction energies and oxygen release, a lot of these different properties. And the one up there is solubility in water for nanoparticles. So this is a far away. From just 15 years, we've gone from single elements to very complicated properties that can be used for things like photovoltaics, thermoelectrics, and energy storage. So the good news is that there's a lot of computation or computation power out there. And the idea is obviously, and you're in this parallelization course, that if we have one material on one computer, it takes a certain amount of time to calculate things like the total energy, the optimized structure, magnetic ground state, charge density. Now if I have twice the number of computers, I can do twice the amount of materials, and so on and so forth. So you can kind of see where I'm going with this. Except for the fact that it's not that easy for us because of the way our codes look and the way the interactions are. If I'm a material scientist and I have a great idea and I want to calculate a lot of different materials, what do? I'm sitting right next to NERSC and I know they have computing calls. So I send in my proposal saying, you know, I like to calculate all these materials. I have my code, it works on my own little workstation, but I now like to put it out on a high-performance computing center. And they're very nice, NERSC, so they give me back lots of course and lots of time. And I go through the cycle of extreme excitement because now I feel like I can compute the universe. Unfortunately, what most of us have gone through is the cycle of, they call it Gartner's hype cycle, that there's a significant valley in one's expectations and then one starts working oneself up from that valley. I'll tell you a little bit of how we did that. The problem is that DFT codes are trivially parallelizable at k-points. But for every single iteration you do, if you basically put out your calculation on a grid of k-points in the wave function space, but after you've calculated the energy for each k-point, you have to bring them all back to calculate the total energy and then spit out a new version of it, move the ions a little bit, move the electrons, and so on. And that collection of data that has to be done every single iteration takes time. And it means it's never going to scale with the number of nodes. You cannot go to 1,000 nodes and cut the time with a factor of 1,000. About 30, 40 nodes, that's I think the maximum what our codes work on. After that, time goes up if you add more nodes to it, to the problem. So it's not parallelizable. And this problem has been the same for the last 15 years. So it can't be an easy one to solve. I always get people saying, but have you tried this? And I said, I haven't. I did my parallelization 10 years ago. Then I think I got 7 nodes then. After that it crashed or got slower. It hasn't gotten that much better today, so I think it's a fairly hard problem to solve. So what do we do? How do we solve this problem? We are not going to fit into the exascale model. The problem is also that we can't predict how long our jobs are going to take. You would think that it would scale with a number of nuclei and electrons because that seems to make, of course, the problem more complicated, but there are other things that matter. The symmetry of the crystal, where the atoms sit, how much I have to move the atoms in order to find the ground state. So the initial guess, for example. This is a collection of, I think, about 10,000 calculations with DFT codes at NERSC. And the number of electrons and the number of atoms, you would think that this would scale with the time that it takes. And the red is basically weeks, green is days, blue is hours. If it was perfectly predictable, then we'd have all the red ones out here. But we don't. There's some red ones down here where you have very few electrons, very few nuclei, and it still takes weeks to get to the answer. So it's not that easy. There's no easy metric that tells us I can bunch my jobs into things that take seconds, weeks, and months. So you've got to deal with stuff like wall times. So what we've done is basically, we have to develop schedulers. We have to develop tools that make it easier for us to run on these large high-performance computing centers. And it's really the inverse of a typical large-scale simulation. So things like climate or Monte Carlo or astronomy, they can just use these nodes over thousands and spit out, and they use the whole cluster for 2 hours, and they get their answer back. I can't do that. I have to run for 2 weeks using 30 nodes to get some of my answers back. So I have to deal with that. There's many ways. I have to deal with restarts. I have to deal with scheduling that some nodes are done and some aren't, if I use a lot of different jobs. Some computing centers won't even let us in because they don't like these small, long jobs. They don't like things that only take 30 nodes and want to stay there for 2 weeks. This is actual data from NERSC, where you can see that there are a number of different varieties, things that take a lot of cores and short time. For example, this job here, and things that take a little bit longer time but few. And the red is people had to wait for a long time in the queue. And the blue are people who got in almost instantly. So you can see that long spike that took up almost the entire cluster for about 2 hours or something. They got in fairly easily because they're prioritized. It's something that they like to, they like things that are tall and long rather than things that are long and or wide and short. They're natural enemies when you want to optimize the efficiency of a high-performance computing center. And that's one of the metrics they report back to DOE for their money. How efficient were we? Were we up? Were we using the cluster 98% of the time? Rather than, because it's much easier to measure that than measure the science that come out of it. That's much harder. How many papers get published? That's one metric, but we all know how bad metric that is. So they tend to report things like efficiency. And that's why schedulers don't really like to combine short, wide, and tall, long jobs, because that means they go down in efficiency. So what do we do when we have things like that? Well, you have to sort of work with them and see if there's any way you can squeeze into the high throughput or the sort of the high performance queue without violating and without making them upset and still getting the throughput you want. So this is where we start. These are the, you've all been where at some sort of amusement park and you can't get into the roller coaster ride because you're not tall enough. No, you haven't been there. I've been there. I still remember that. It was a long time ago, but still. That's kind of the same with these high-performance computing queues. You have to be long and tall to get in. And we're over there. We're the high-throughput material science people, and we're all very short. Maybe a little thick, too. That would sort of complete the picture. Whereas combustion modeling and climate simulation and astronomy guys, they just walk right through. Why do we care? Well, we care because this is huge, right? NERSC offers us 40 million CPU hours a year. That's what the materials project gets, and it's a huge resource. If we were to do this on a 16-core workstation, it would take us 285 years. So this is worth it for us. We have to get in there somehow, because it really can accelerate the kind of work we do and the number of materials we can compute and the number of properties we can lay our hands on. So we really have to get across this in some way. So we have to work with small jobs, the queue job limit. I think most computing centers only allow you to have like 10 jobs in the queue. We'd like to populate it with thousands, because that's how we work. Single sort of parallel, single submissions of one job rather than one job over 1,000 cores. So we need to play by their rules and their wall time limits, which are designed for something completely different than what we do. So what we do is we mask ourselves. We get up and we stand on each other's shoulders and we package 1,000 jobs into one and then spit it out on 1,000 divided by 30 cores or nodes. That's how we do it. And it kind of works, and they know that we do this, and they're not upset with us. But some places wouldn't even consider this because it requires communication between those 30 nodes, but not all of them. So it's not really the idea of the computing center, but still, it does work. So this is how we solve it. Okay, assuming we solve this problem with the computing, which has worked with NERSC, but I'm not going to say it works everywhere. I'm working with the ALCF in Argonne too. They have Blue Gene, which is a lot more complicated than NERSC, and they built a slightly less flexible system than NERSC has. So in that case, we actually have to change the infrastructure as well. So I'll give you some examples of what you can do once you have this enormous amount of computing at your fingertips. The first example comes from alkaline batteries. So in 2005, this is where we started to do the first high-throughput materials design exercise. I'm sure you guys all use these little AA alkaline batteries, non-rechargeables. You throw them away in the garbage when you're done with them. Duracell makes them, the little Duracell bunny, or that's the Energizer, sorry. Anyway, same kind of battery, and which are owned by Procter & Gamble. And they came to us, I was at MIT at the time, and they came and asked us, is there anything better out here than the current chemistry we're using? So these guys uses a very old chemistry. It's manganese dioxide in very alkaline solution, zinc Drano, the stuff you pour down the drain when it's clogged, and a zinc anode. It's a very old technology, but they're making a lot of money on these. So they didn't want that market share to be absorbed by somebody coming up with something better. So they asked us, can you compute if there's anything better out there of all the known materials in the world and beyond. So that's when you take a big breath and you ask for a lot of money, and we got 1 year to do it. We knew how to compute a lot of the things they were asking for. We knew how to compute phase diagrams, for example, like this one. This is what you're doing when you have a non-rechargeable. You start at a highly charged state, and then you discharge it through the phase diagram, and you end up with something that's a metal-like or a binary. And you can compute voltage profiles and capacities and stabilities of all the different materials that this sequence of reactions go through. But the one thing we didn't know in the beginning was, how do you calculate for stability in very alkaline water? Basically like sluggish, pH 15, really, really corrosive stuff, like Drano basically. So that was one of the things we had to develop, a methodology that rapidly could screen thousands of materials for dissolution. And we ended up taking an extremely pragmatic approach, because some of these things are not easily captured by first principles. We actually combined experimental information with computed solids. So experimental aqueous ions with computed solids. And these are some of the results. These are Courbet diagrams. It tells you what the stable phase is in water, or as a function of pH and potential. So this is something that was very useful, because now we can actually compute which solids have a chance of being stable at pH 14 or 15, which is where the alkaline ions or alkaline battery chemistry sits. In the end, what we did was we took the known compounds of the world, inorganic compounds. There's about 30 to 50,000 known, depending on which database you're going to. We permuted them, we substituted them, we looked at different kinds of combinations of them, and in the end, we screened over 100,000 using data mining, and 10,000 by actual first principles calculations. In those days, 10,000 was a huge number. Getting through 10,000 in 1 year was a significant effort, and it took a large computing center somewhere in the Midwest that Procter & Gamble gave us full access to. But the idea is not that you screen all these on day one. You basically start calculating a few thousand, you learn from those, you data mine, you throw in new versions, and you go around in a cycle until you have a bunch of candidate materials at the end that you really like from all different properties that you can calculate. And then you give some candidates to the experimentalist, and you hope for the best. The best usually doesn't just fall out of the funnel. I get that question a lot. Well, you throw the world of possible materials at the computer. Does the best one just sort of come out one day? No, it typically doesn't. What you learn is you learn a lot of materials design rules. And you form maps like this where you combine different properties and you see, how do I have to do trade-offs in order to combine these things? This is a map that shows us stability. If you combine one cation with another cation in the periodic table, so think, for example, sodium plus with manganese 4 and oxygen, are you going to get a stabilization energy on average by combining those two cations in an oxide? The green dots tell you where you do on average, which element, which cations like to sit in the same structure. The white dots tell you there's really not much gain, and the red dots tell you those two guys hate each other. Don't ever put them in an oxide together. They're going to fall apart and form something else. So that's something how we learn how to stabilize solids, especially with high valence redox active cations. We also learned that most things dissolve. This is a data mining map that talks about which cations have a higher dissolution energy than others. If you want to stabilize a ternary oxide to be stable in these batteries, you have to learn which cations like to sit together, and also they cannot dissolve too much, either one of them. And they have to be redox active. You have to get a lot of energy density out of the air. So you're starting to see all the different properties that you can optimize and how some of them may actually not correlate that well with each other. In the end, we screened more than 100,000 compounds. 1,500 of them were better than manganese dioxide in the alkaline cell. So that wasn't actually such a hard problem. It was fairly easy to find compounds that had a higher energy density, that had a better voltage or capacity or a combined version of those. 200 of them had even a chance of being stable in the aqueous, in the KOH electrolyte that these little batteries were. And they really wanted a drop-in replacement. They don't want something that that you have to change the anode for, or you have to change the electrolyte. That's costly. So they wanted a drop-in replacement for the cathode. You can see here from the table that they are doing fairly well. These 200 compounds, some of them here, compared to the manganese dioxide that they're currently using. So Duracell have patented a lot of these. These are very broad patents. They basically include everything, because obviously they, again, remember they wanted to blanket the space to make sure that nobody else can make something better. But they also wanted to develop the next generation of these things, and I'm happy to say that they're working on one of these. And it actually does work, one of those 200 compounds. It's about twice as good as what's in these. And I'm still working with them, so they must have been fairly happy. Hopefully one day they will commercialize it. You know, the clock is ticking, remember 18 years, and this started in 2005. So if we're to beat that timeline showing that computations can really accelerate this, not just come up with better materials, but also be better at predicting which one you should take out of that pool of 50,000 materials so that you have a shorter timeline getting to commercialization. But hopefully we'll get there. It's few kinks to iron out about stability, but otherwise they're pretty much there. So this was a very successful project in 2005, 2006. We got very excited. It was the first time we'd shown that high-throughput computations could really lead to novel design in material science. So then, of course, you want to do it for other areas. You want to do it for example, lithium-ion batteries. Those guys are rechargeable. They have to last 10 years, right? At least if you want to put it in a car. I'm totally dating myself by this slide, right? I'm a big fan of Back to the Future, 1989. You remember the quote by Doc when he talks about the DeLorean? He says, no, this sucker is electrical, but I need a nuclear reaction to generate the 1.21 gigawatt of electricity. I don't know if any one of you own an electric car. It's not quite 1.21 gigawatt of electricity to get an electric car going, but they do need a lot of energy. If you've got a Nissan Leaf or a Prius or something, you know that you don't really get that far. So this is sort of a back of the envelope. Small car, you get about 4 miles per kilowatt hour. If you want 100 miles out of your battery, you have a $10,000 battery with today's cost of materials on the lithium-ion battery. It's a bit too much for a car that normally costs $20,000. You're adding now another $10,000 to that normal-sized car. And if you want a bigger car and a bigger battery, it gets worse. And you'd like to drive longer or further than that. Most people are not okay with buying a car that only goes 100 miles, because then they have to have a second car or a third car that will get them to, when they want to go on vacation or they don't want to feel that range anxiety. And the way to solve this, you could try to slash the cost of the engineering, but people try to do that, and it's, you can only get so far. So if you want to really make an impact, the way is to really find materials, just like in the alkaline example, that have a higher energy density, or that are much, much cheaper, but that's going to be tough because there's a limited amount of the cations you can use in these materials. It's typically only the redox active transition metals that's going to work for you. So you got to find something that does better. Same kind of problem, but different kind of application. We use the same methodology. This was sold to 2 other companies, Umicore and Bosch, that wanted to pay for finding novel materials for lithium-ion batteries. These are some of the ones that were made. They're pretty colors. These are the manganese not just the manganese, but the carbonophosphates. They're based on substitutions of a fairly rare mineral called siderenkites, and they were completely designed in the computer using this methodology of screening, learning from the data, and coming up with new materials. Since then, we have done it for alkaline batteries. We've done it for lithium rechargeables. I'm not going to say that any of these are currently available in the market, but some of them have a potential to get there. And lately, we also applied it to transparent conductors, the little thin film that sits on top of solar panels, for example, that needs to be able to transmit electrons but are transparent to light. So it's not just for batteries. This approach of screening materials for whatever properties that you can calculate can be important for many different kinds of applications. So now I'll talk about the materials project, which is a publicly growing resource, and it's freely available. It's in the spirit of let's try to disseminate as much as we can of the kind of materials data that we produce anyway. So remember we talked about the Edisonian approach, where you make a material, or you buy it in his case, and you test every single one until you find the one that works better than the other. And this idea of screening in silico, where you take all the different ideas. You don't have to buy them, you don't have to make them, you just put them in the computer, and at least, the very least you can do is screen out the bad ideas. And even that is a huge efficiency gain. And not just for energy storage, but for whatever you want to do. And hopefully, in the end, what you do is give a better candidate to your experimentalists, so they don't have to spend all that time synthesizing, buying, making, testing, which is hugely inefficient. So what we decided to do is that we would take all the data that we had produced over the different kinds of projects, for example, the alkaline project, the rechargeable lithium-ion project, and whatever else we were doing, and say, okay, we're going to give this to the public, because they can do cool stuff in areas that I can't imagine. So right now, the Materials Project, we've been online since 2011. We have a little bit more than 49,000 calculated compounds available. It's growing usually monthly. We have a new release because our computers never sleep. We are always calculating something at NERSC and other places. So we tend to put out new releases for new data, either by just using our own ideas of what can be out there. So there's not just known compounds, but also other versions of it, substitutions, things that we think would be a good idea. And we have multiple tools that we have generated ourselves on how to analyze the data. For example, we want to build phase diagrams, we want to build voltage curves, we want to build models of local environment, or other kinds of data that you want to analyze and screen on. If you look at the Materials Project, there are a number of these different apps. That's the tools. You can, I'm not sure you can see them, but the tools are currently battery properties, if you want to look at lithium-ion battery properties, phase diagrams, Courbet diagrams, those are the ones that we're talking about, aqueous stability. Reaction calculator tells you whether you can combine whatever compound with another compound, if you're getting energy or if you're losing energy, if you have to import energy to do it. And all these things are freely available. The only thing we ask for is an email address and an affiliation, and frequently people make it up too. We have a few Mickey Mouse and other people registered with the project. So what we've done, not just to, remember we made this work on the supercomputer, or the high-performance computing centers, but we've also tried to make the process from idea to actual calculation as easy as possible. So we've developed a workflow code base that takes care of most of the mundane parts about submitting a structure or submitting an idea to the calculation. This is where most of us spent our time in the old days. First you have to generate the input files, then you have to map it on some sort of, what different tasks am I going to perform? I'm submitting to a supercomputing center. I have to have some sort of error handling, because none of these codes are perfect. They frequently crash, or there are errors, or they don't converge. So there's the sort of self-healing error handling over here, file transfer, and file parsing. And all this is taken care of a code that we call Fireworks, that is agnostic to what kind of calculation you want to run. It's not just DFT codes. You can use it if you want to do some other kind of workflow. You just have to modify it. It doesn't really care what you're doing, as long as there's a way of making it modular. So right now we have the situation where we have an idea, and we are fairly much where we can just push a button, submit, and it goes to the cluster, and we get data into our database. So the dynamic workflow that Fireworks is based on is that you can design things like this. If you want to use Fireworks for something else than what we're doing for it, you can design things like detours, insert new steps based on whatever result you got on the first one, branches, additions, and duplicate, job detection. It's supposed to be basically adaptable to whatever workflow you want to do. And I know people have done workflows in a lot of different areas, but this one seems to be working fairly well for us, and a couple of other groups that do fairly different things. It's hosted on GitHub, so if you want to check it out, feel free. We have a few people in the community. This was released last year, so it's not that it hasn't been available that long, but the different tasks that we do is structure and charge and DOS, density of the electrons, the band structure, optical properties, phonons, spectra, more advanced calculations. And basically the idea is that you modularize as much as possible. Because remember, again, we have to fit into the queue structure and the wall time of the supercomputing center. So we don't want to have a long line of tasks that just sequentially operate no matter what. We want to make sure that if something finishes, that we take care of that by itself. And then we we submit the next version of it and the next version. So as modular as possible is good if you want to fit into the 2 weeks of wall time you typically get. If you have your own cluster, you don't have to do this. You just submit a long line of jobs, and they can run for however long you want to. But on the other hand, then you won't get to the kind of data that we're getting, because it will take hundreds of years. This is the infrastructure that we currently have developed. I would say this is version 3. We started in 2005 with something that was very, very simple. It was command line getting into the database. Now it's much more sophisticated. We've changed the languages a couple of times as well. We moved from a different database language to a document-based database language called MongoDB, because the one thing we realized we needed more than anything was flexibility. This is very much a moving beast. Every day we realize we need something new or something different, a different schema, a different connection between different database tables, so things need to be as flexible as possible. But the idea is that we take structures from wherever we can get them. Remember the initial starting point of the ions and the electrons, from ICSD, from databases, from user submissions. We process them, we transform them into a database. We go through the workflow manager, and that contains 3 different kinds of codes. We already talked about fireworks. That's the workflow management. There's a custodian, that's the self-healing guy that takes care of all the errors, and that's specific to the code you're using. If you're using a solid, for example, VASP or something like that, you have specific errors you take care of, and you have to write that customized. If you're using lamps, if you're doing some other kind of atomistic code, you want to use your own custodian. And then PyMatGen is the analysis software. These are all freely available codes. You can go and check them out on GitHub. They all have specific guardian angels, as you can see, that take care of them. So part of my team, we're fairly nerdy, so of course we're watching a lot of movies, and we're all the Avengers. You can guess who I am in the Avengers. And then, of course, we post-process, we error check, we make sure after we've run all these, and we have an analysis software, the PyMatGen one, and then we disseminate it through the web or the API. We tried really hard to move away from the academic code development model where you develop for yourself, fast and dirty. I just want to get something working. I have my thesis, I have my paper, I'm just going to get it done, and then when I move on, that code is going to fall into disrepair and nobody else is going to want to work with it again. I'm sure you guys have all experienced that to one degree or another. We're trying to build software that lasts, that actually can be used by other people as well, and that doesn't have a huge barrier to being useful. So our software management philosophy is that it's all open source, which is great. You get more eyes on the code. It also puts more demands on how it has to be readable. You cannot have variable names of your favorite pop groups. It has to be something more intelligent than that so that people can use it and understand it. When you say to people this is going to get distributed over the world, they tend to think a little bit more carefully about the structure of their code. We have benevolent dictators, as you see. These are all the Avengers. Captain America is a lot more nice than the Hulk. That's true in its team too. You don't really want to aggravate the Hulk. And we try to have very clear documentation to prevent code rot, to attract more users. We all know it's a huge barrier to use somebody else's code and develop within it. Most people would much rather write their own. But once it becomes like a fairly large resource and you can see, oh, well, learning this code, I get so much for free. And then I can just add my little snippet to it and it becomes worth it. And it's great to see how that's actually happening. First, when we put this out there, most of the people around me said, oh, you're just giving advantages to other people. What are you really getting back? And in the beginning, you get absolutely nothing back. Most people just take it, download it, and you never hear from them again. But after a while, people start contributing back. They start asking questions. Why have you done it this way? I have this kind of algorithm. Can I implement it? Is that going to make your job better? And it actually does. So open source is a great way to go if you have the sort of patience for it and can motivate your team to go the extra mile to make it readable to other people. So I can really recommend that. We're seeing the benefit of it. This is a little snippet of a discussion that happens every day on GitHub and the related resources where people are just asking questions, going back and forth, trying to see what makes sense in the next development or release of the code. This is a little map saying or talking about how what parts of the world are using PyMethane currently. PyMethane has been released for about a year more, so it's a little more mature than Fireworks. Obviously, there's large bases in the US on the West Coast and the East Coast, some in South America, obviously Europe, big user. There's a dude in Nigeria that really likes our stuff. I don't really know what he's doing with it. Same thing goes for Australia. Never heard from them, no idea what they're doing, but it's pretty cool. And obviously also Asia, Korea, and China. So not only do we distribute the codes, and we're starting to get something back for that, which is great, we also distribute the data. And you've seen the web interface. That's one way of doing it. But if you want to access the Materials Project data, you can do it in different ways, depending on your level, what you want to get out of it. The first thing is you can go directly to the database, which isn't the best way, in my opinion, but it's obviously very flexible. You can get anything we have in the database. On the other hand, you're vulnerable to, if we change the schema, if we change anything, then your scripts that access it will break. So it's a bit fragile, but our developers tend to do that. You can go through the web application, which is the nice interface that our web developer has designed, where it's easy to use. It's supposed to be as user-friendly as possible, given that it's still a specialized area. If you have an experimentalist, that's one of our target audiences. We want experimentalists to be able to use our data, not just theorists. So we're trying to make the data as accessible as possible, and that the search functions are something that any material scientist can relate to, not just theorists. Obviously, it's also not flexible enough if you want lots of data. If you want to data mine your own, you have your theory that voltages correlate with a certain, local environments in manganese oxides. You don't want to sit and click on the web interface, 20 or 30 or 100 or 1,000 times to get all that data. So for that kind of access, we have the Materials API, which is a RESTful interface, where you can just go straight into the database and you're not exposed to the fragility of using the database schema. And I'll give a little bit of examples from that. So the REST API basically uses a URL resource. You can do things like get, post, put, delete, and it's all done through, you can get a secure ID through the web interface, and then you can just post it as a URL. And the response is usually a JSON. It looks pretty ugly, but it's easy to parse. So this is an example of how you can access it. You just basically put in the materialsproject.org, REST version 1, and then you have the preamble, the request type. You want, for example, if you want all the different Fe2 or 3 energies, not just one, then you will get it through this kind of call.
Question?
Yes?
So are users expected to post their data, even if they're commercial companies?
So we have so far not opened it up to the two-way traffic, but we can. And we're exploring how to do that right now with other entities, mostly in the academic world so far. We've been trying to build company collaborations, but it's a very difficult way to go because of IP, because of trade secrets. So it's mostly one-way traffic for now. But there are lots of companies that actually do use our website. And they give out their names. In most cases, we don't find out what they're interested in. And we actually have a privacy policy saying that we never correlate a specific user with what kind of searches they do. Because then they would just shut, they wouldn't allow any of their engineers to do anything. So if I find out that Procter & Gamble is doing 10,000 bismuth searches, then I might go and buy stock in bismuth mines. It's, the data can be used for a lot of things. I think we know that in the information age. So they're very sensitive to that. But we do feel very strongly that just as the codes, giving out data for free is amazingly powerful. We know that from the information age and from Google. People do really cool stuff if they get their hands on data. And we're just seeing the beginning of that in the Materials Project. If you give out data, they will do things you never expected to. And we're only the 2 groups or the 3 groups that started this. We could only do so much with the data. In the end, when we give it to other people, they will have other ideas. They will interact with other companies, with other applications, and they will use the data for other things. So hopefully we'll create a little bit of a materials ecosystem, and people will start contributing not just algorithms back, but also data. So the Materials Project is a rapidly growing resource. Like I said, we launched in October 2011. We have a number of different grants. We have more than 6,600 registered users. And I know from the perspective of Twitter and Facebook, that's not really that impressive. But in the material science community, it's not so shabby. And what I get really excited about is that somewhere between 100 and 300 different users use it every day. So it really is a live resource for people to use as a lookup. You can search for material, you can look at its properties, you can look for what kind of properties correlate, across chemistries, and do your own get your own insights about how materials work, what kind of chemistries are important for certain applications. It's being used in courseware. Students nowadays, like you guys, are much better at using a web interface and just clicking around and trying different things. It's a much better way of, for example, learning phase diagrams than looking in a book. Because you can try different things. You can try what happens if I use high oxygen chemical potential, high temperature, low temperature, what kind of phases can I make under different conditions. And companies are using it too. Most of the time I have no idea what they're using it for, obviously. And we also see that while our user trend has been a bit fluctuating in the beginning, when we had releases, lots of people came on board. For about 2 years, we were linear in the increase of the number of users, but the last 6 months, it's been going exponential. So clearly, people are telling other people about this cool resource, and that brings more people to the project, which is great. So I'd like to end with the vision of where we're going. Facebook may not be the ultimate goal, but we really do believe that we can do a lot better than we've been doing in the past. Researchers in academia, we tend to sit with our own toolboxes and come up with our own ideas. And sometimes we work in teams, but it's teams that self-assemble to some degree, and we come up with whatever materials we want to do. But if we work together, if we actually use the information technology that's out there and not just publish on paper, but we actually give our data to the rest of the world, I think we can accelerate materials discovery like we've done in our group, but we can do better than that. So if we all share the data in some way, in some searchable, accessible way, then hopefully we can go towards what they call the materials genome. So that kind of concludes my lecture. I'll be happy to take any questions.
I have a question, which is some of the other folks I know at LBL who do different kinds, I think, of density functional theory do try to scale up to lots of processors and explore different kinds of algorithms. So what makes your particular DFT calculations different from some of these other ones which seem to want to scale up to thousands of processors?
Yeah, so I think you can do it in certain more restricted spaces. I think, for example, if you do a kind of more of a coarse-grained or multi-scale modeling of a problem, and you make your part of your material coarse-grained compared to other parts, I think you can do it. As far as I know, there is no ground state DFT code that works today on lots and lots of nodes. You would have to make approximations on some other version of it. For example, if you neglect certain interactions, you can scale up to much higher number of processors.
So can you say a little more about what the bottleneck is that's keeping it from scaling?
Well, it's really that communication part. And if you know that the matrix you're looking at of interactions isn't sparse in any way, then it's really hard to block out pieces. You can do that, then you are neglecting certain interactions. But if you don't neglect them, or you try to be as accurate as possible, then it's really hard to. You really can't get around the communication bottleneck.
So, which is to assemble the.
Yeah. So assemble all the information from the different K points that you have as a grid over your space in the wave functional reciprocal space. And you try to pull those back. You have to do that every single iteration to get a new energy, and then to move the ions a little bit, and then get a new energy and move the ions a bit. So finding the ground state of both the ions and the electrons is a successive iteration of minimizations, basically.
So we'll be, on a related note, there's a new faculty member who will be joining us next year, Lynn.
Oh.
who's also affiliated with LDL, who works on faster parallel algorithms for density function.
Very
theory.
cool.
So it'll just be interesting to see how that works.
I'm always open. It would be great if it could be made to work. I know a couple of colleagues of mine too that have tried to make it work. So far, I haven't heard anything from the community that there is a faster parallelized version of any of these, especially the commercial softwares that are out there. So yeah, no, that'd be amazing.
So, any more questions? So let's thank the speaker again.